In this lesson, we shall look at chemical equilibrium, or what sometimes is called chemical equilibria. We will go through the theory and also spend time on past examination questions. And we proceed. Right, understanding chemical equilibrium is very important for examination purposes. So to start with, we're often interested in what we call open systems and also what we call closed systems. Okay, now what is an open system? Right, so in an open system, matter and energy can leave the system. Okay, if the system is open, it means that matter and energy can leave the system. But in a closed system, matter and energy cannot leave the system. Now, for a closed system, a dynamic chemical equilibrium will form when the rate of the forward and reverse reactions are equal. Okay, for a closed system, a dynamic chemical equilibrium will form when the rate of the forward and reverse reactions are equal. Okay, so this offers us an opportunity to define what we call a dynamic chemical equilibrium as that which forms when the rate of the forward and reverse reactions are equal. So when we then say the rate of the forward and reverse reactions are equal, then we have what we call a dynamic chemical equilibrium. There's something called a forward reaction. And in a forward reaction, reactants change into products. So now we actually obviously have an example where you have, for instance, two hydrogen atoms and two oxygen atoms, and there's a forward reaction which is in the direction of the blue arrow, and you are able to see that now you have two hydrogen atoms and one oxygen atom there. And now the reverse reaction, in the what we call the reverse reaction, products change into reactants. So when we go in the direction of the green arrow, the products change into reactants. What are we seeing here? We are seeing that hydrogen and oxygen produce water. They produce H2O. H2O. All right, so they produce H2O, meaning that a combination of hydrogen and oxygen produces water. But now, reverse reaction implies that the products change into reactants, meaning that if you have water, you can be able to break water down. Very technical process, though. You can be able to break water down into hydrogen and oxygen. Okay, not very easy to do that. Okay, but now many chemical reactions are reversible. Let's take a look at that. Let's take a look at that. Okay. Now, a system is a chemical equilibrium. Now, we are looking at what a system is precisely. What is a system? A system is a chemical equilibrium when the rate of the forward reaction and reverse reaction are equal. All right, a system is in chemical equilibrium. When is a system in chemical equilibrium? When do we have what we call the chemical equilibrium? When do we have that? Right, so a system is in chemical equilibrium when the rate of the forward reaction and reverse reaction are equal. Okay, so we're defining here what we call chemical equilibrium, and that occurs when the rate of the forward and reverse reactions are equal. Okay, we're good. Let's continue right now. Let's see what more we have here. And see what more we have here. Okay. If you look at the forward reaction, the forward reaction is the one that is dotted, and the reverse reaction is solid line. And we have the rate in the vertical axis and the time in the horizontal axis. Okay. Now, this is actually what we're seeing. So, looking at this diagram here, looking at the rates on the vertical axis, we're able to see that the forward reaction is certainly the broken one, and the reverse reaction is solid. But also when the rate of the forward and reverse reactions are equal, so now they're equal at this point, because this is the rate axis, so they're equal at this point, meaning at the time that these converge together, that the rate of the forward and the reverse become equal to each other, then we have what we call chemical equilibrium. Let us continue and analyze more concepts. The notion of what we call the concentration of the reactants and products are constant. Okay, let us look at, so now we're defining chemical equilibrium when the concentration of the products, of the reactants and products are constant. So during what we call a chemical equilibrium, the concentration of the reactants and products are constant, meaning that you have the concentration axis as the vertical axis and the time as the horizontal axis. But what we are seeing is therefore that now the reactants and products will have constant concentrations. So their concentrations are constant. So now, in other words, the concentration of the reactants and the concentration of the products remain constant. It doesn't mean they're equal to each other, but it means they are constant. So during equilibrium, something happens. The concentration of the reactants here. So you can see now the reactants now start from the origin and the products start up there. But what we are able to see, therefore, that the concentrations would therefore become constant, meaning that these will go horizontally quite for some time. Okay, or at least indefinitely. Okay, so we have looked at the rates and the concentrations. Okay, now it's very important for us to have a very clear understanding of Le Chatelier's principle. Right, so it's very important for us to have a clear understanding of what we call Le Chatelier's principle as we learn it, but also in a way that will allow us to understand and also be in a position to interpret this and use it in the exams. Okay, understanding Le Chatelier's principle. Basically, an equilibrium system will respond to reduce the effect of the change by favoring either the forward or reverse reaction. Okay, let us look at this sentence again. Basically, an equilibrium system will respond to reduce. So an equilibrium system will respond to reduce the effect of the change. In other words, if there is a change, we are saying the equilibrium will respond to reduce the effect of the change by favoring either the forward or reverse reaction. Now, think of Le Chatelier's principle as follows. Think of Le Chatelier's principle. So this one must be principle, please. Right. Think of Le Chatelier's principle as a seesaw. As a seesaw. You have the rate of the forward reaction, rate of the reverse reaction on this side. We have the reactants here and the products. Okay. So when the reactants themselves, for example, the rate of the forward reaction and the rate of the reverse reaction are equal, where you have the reactants and the products. Therefore, there is a balance. So what we call the seesaw is balanced. Is balanced. Okay, good. It's balanced. Now, next, let's look at an example of these. Le Chatelier's principle. Now, a factor causes a change to an equilibrium system, increasing the concentration of the reactants. Let us look at this now and the factor here. So here's a seesaw example where the rate of the forward reaction now is actually such that, according to this description here, this side is heavier because the reactants increased. So you are then saying increasing the concentration of the reactants. So if you increase the concentration of the reactants, you can see that this side is heavier. And if this side is heavier, it means that now the reactants have their concentration increased, and the products therefore would actually somehow have less relative to the former state, because now we have just increased the concentration of the reactants. In response, the forward reaction is favored, decreasing the concentration of the reactants, restoring a new balance. Okay, let's look at these and look at these carefully. Right. Now, we are looking at what happens if we just decide to increase the concentration of the reactants. Surely, if we increase the concentration of the reactants, we can see that this is not balanced, because this side is heavier because the reactants increased. So the reactants increased. Now, when the reactants then increased, we have that therefore their concentration increased, the concentration of the reactants increased, and therefore they're sort of heavier. And if they're heavier, then you really can see that this is not balanced. So what does Le Chatelier's principle therefore say? In response, the forward reaction is favored, okay, because you increase the reactants. So according to Le Chatelier's principle, an equilibrium system will respond to reduce the effect of the change by favoring either the forward or reverse direction. It will respond. Okay, so an equilibrium system will respond to reduce the effect of the change by favoring either the forward or reverse reaction. Increasing the concentration of the reactants in this case, in response, the forward reaction is favored, decreasing the concentration of the reactants, restoring a new balance. Next. Okay, let us speak about Kc. Right, let's talk about Kc and what Kc means here. And what Kc means here. Right, what Kc means here. Okay, the equilibrium constant is the ratio of products to reactants. What is Kc? It is the ratio of products to reactants. Products to reactants, that is Kc. Okay, that's the definition. If somebody would sort of ask, what is Kc? Kc is the ratio of products to reactants. It allows the chemist to determine the progress of a reaction, indicating whether the formation of the reactants or product is being favored. For the chemical reaction at equilibrium, let's look at this chemical reaction at equilibrium. It's just a hypothetical chemical reaction there. Let's see what happens to it as we analyze this very, very carefully. Okay. Now there is lowercase a and capital A, and then we have lowercase plus lowercase b, capital B, in the forward and reverse. So the forward and reverse reactions are taking place. And we have lowercase c and uppercase C plus lowercase d plus uppercase D. Okay, now we have the ratio of the concentration of the products and the reactants. Okay, yeah, right. So the ratio of products to reactants, products themselves. So you'd have therefore that the concentration of C to the concentration of the element or of the compound C to the power lowercase c, the concentration of D to the power, the coefficient D, which occurs when this is balanced, when the chemical equation is balanced, divided by the concentration of the reactants. The reactants are the concentration of A to the power A times concentration of B to the power B. There are phases of matter. Right, phases of matter are important. Okay, so because now we speak about the phases of matter, now we do not include all of them in the Kc calculation. So which phases do we include in the calculation? Let's take a look. There are pure substances which are liquid or solid, do not have a measurable concentration. Pure substances, which we refer to as liquid or solid, do not have a measurable concentration and are given a value of 1 in the Kc expression. This we call homogeneous. So yeah, the liquids and the solids, we give them concentration of a value of 1. there's what you call the homogeneous reactions and heterogeneous reactions. So we are speaking about two types of reactions: homogeneous versus heterogeneous. Right? Reactants and products are all in the same phase. When we have the what we call homogeneous reactions, we speak about the same phase. Homo means same, right? So same phase. So now the reactants and products are all in the same phase, where you have that AA plus BB in the forward and reverse, CC, and all of these are in gaseous states. And therefore, obviously, this gives us an example of what we call a homogeneous reaction because all of these are gases. Now, let's look at the next one. Looking at the heterogeneous reactions, the reactions and products are not all in the same phase. Okay, so now we have AA plus BB, forward and reverse reactions, and you have CC plus DD. But you can see A is in the solid state, B is in the liquid, and C is a gas, and D is in the aqueous state. Okay, good. It's in the aqueous state. Right. So this is then all right. This is then all right. Okay, we're good. Let's continue. But now what we're noting here is, okay, A is in the solid and B is in the liquid. So now we have C in the gaseous state and D in aqueous. So now the Kc is going to be exactly this way, but now we take the concentration of the products because Kc is the ratio of products to reactants. Okay, if this is true, then what do we do with this? Right, we note that the liquids, which is this here, and the solid A and the liquid B would obviously be not be included, won't be included in the Kc there. That is the point we're raising. We continue and analyze. Now, this is strong, but very powerful. Only temperature can change Kc. This is it. Only temperature. What about pressure? What about concentration? What about this? What about that? Only temperature can change Kc. This is the claim. So now, if they ask you, will the Kc change? So it's only temperature. Only a change in temperature has the power to change Kc. The value of Kc does not change if a catalyst is added. Somebody can come and say, okay, the examiner, we're going to be looking at a lot of exam questions. I have tons and tons of questions we're going to do today. But the value of Kc does not change if a catalyst is added. Concentration of reactants on products change, or pressure of the system changes. Okay, so now somebody can come and say, what about if we change the concentration of the reactants or products? We say the Kc doesn't change. What about if pressure of the system changes? Kc doesn't change. Okay, what about if a catalyst is added? So we're looking at a catalyst, we're looking at concentration, and we're looking at pressure. We're saying all these guys, they don't have the power to change Kc. All these factors do not have the power to change the Kc, but only temperature can. Okay, let us look at understanding the value of Kc. Okay, so now the Kc value itself, we can see three parts of the story. Three parts of the story. For example, Kc is equal to 1. It happens that Kc is 1. It happens that Kc is what? Kc is greater than 1 or it is less than 1. Okay, now we continue. Right, we continue. When Kc is 1, the concentration of the reactants and products are about the same. When Kc is 1, it means that the concentration of reactants and products are about the same. That is why it's 1. Because obviously we know that the Kc itself is the ratio of products to reactants. So if the concentration of the products and reactants are equal to each other, then it's like saying a number divided by itself, like 2 divided by 2. It would just be to just be 1. Okay, when is the Kc greater than 1? Because sometimes it's greater than 1, this Kc, when we do that, like we,
So isn't it
yes,
one when it's solid or liquid?
yes, yes, the concentration, yeah, obviously when it's solid or liquid, it's 1. Obviously because as I said here, like the pure substances which are liquid or solid do not have a measurable concentration and are given a value of 1. So the individual concentration, like the concentration of a solid, like the concentration of, what is the concentration of A here? We don't include it because we just say 1 because it's a solid. So the individual concentrations, we put them as 1 there. So yes, I agree with you. So obviously, if we're dealing with solids, then you would be dividing the products and reactants which are in solid. So it's gonna be 1, 1, 1, 1. Okay, but we can have a case where there is a solid, but not only a solid and a liquid. Okay, for example, let's look at this. Right. So you can have, when would this concentration be 1? In the heterogeneous reaction case, for example. So you'd have that the A is a solid, so its concentration is 1, and the B is a liquid, concentration is 1. And then now, meaning that you are saying concentration of products over reactants. The reactants in the denominator will have concentration of 1. The denominator will have concentration of 1. So obviously, if the denominator is concentration of 1, well, we expect the products also in this case, because the products and directions. So these guys will have concentration of 1, but the products we don't know. Meaning it can be anything. Okay, it can be greater than 1. It can be equal to 1 if they're equal. Or it can be more than 1. Okay, but my point is, we would say at this point, the concentration of A as a solid is 1. And the concentration of B, we are sure, because it's a liquid, is 1 as well. Okay, so that's what we're saying. All right, yeah, we're gonna look at it more in detail as we look at the exam questions. But yeah, just take note of that at the moment. It's very, very interesting. Okay, let us analyze this. Yes, I was saying that yes, we can have that the concentration is the concentration itself is 1, like the Kc, excuse me, the Kc is 1 when you are dealing with solids or liquids, but moreover, we are able to say, right, we're able to say that it can be 1 in other cases as well. It can be 1 other cases, but when dealing with solids and liquids, you are 100% sure that it's going to be 1. Okay, but when is the Kc bigger than 1? So we are saying concentration of reactants and products are about the same. So they can be about the same even if we are dealing with gases, or we are dealing with aqueous substances, or substances in the aqueous state. Right, so when is the Kc bigger than 1? The concentration of products are higher than reactants. Okay, yeah, because this makes sense. Because when the concentration of the product, when the numerator is bigger, you're dealing with the Kc calculation, and you have that the numerator is bigger, 2 divided by 1 is 2, so this is bigger than 1. And that would be true when the concentration of the products is certainly bigger than the concentration of the reactants. When that happens, we have that the the Kc is bigger than 1. Okay, we have that the Kc is bigger than 1. When is the Kc smaller than 1? When the concentration of the products are higher than, of the reactants are higher than products. Okay, so yeah. So in other words, this would be that we're dealing with Kc. And dealing with the Kc now, we're looking at this particular concentration of the products divided by concentration of the reactants. So we're dealing with concentration of the products, and we're dividing with the concentration of the reactants. Right. So if we are saying therefore now the Kc is smaller than 1, that would mean therefore that you are having that the concentration of the products is much less than the concentration of the reactants. So that the reactants have a greater concentration, because if they have a greater concentration, maybe this one is 2. And then the reactants will have a greater concentration, maybe 3. Okay. Right. Or now we have 2 and then maybe 4 there. Okay. And the 2 or 4 is like a 0.5, for example, which is like 1/2 of this one. So yeah, you'll be able to see that it is the 1/2 is smaller than 1, meaning that after the case is smaller than 1, when the concentration of the reactants, concentrations of the reactants are higher than products. Right. So you can even put S here to mean concentrations of reactants and products are both the same. Concentrations of products are higher than reactants. Concentrations of reactants are higher than products. So obviously, if the concentration of reactants are higher than products, okay, so your denominator is bigger. If the denominator is bigger, like 2/4, or like 2/3, bigger denominator, then the answer is going to be 0 point something. So which is smaller than 1. Ensure you know how to calculate the concentration or the concentration and moles. Okay, these ones we need to remember them. That concentration is number of moles over volume, and the concentration, for instance, is measured in moles per decimeter cubed. But also need to remember, so concentration and moles. How do we find the moles? Okay, right? It's mass over molar mass. Right, it's mass over molar mass. So it's the mass in grams divided by molar mass in grams per mole. So, and the N is the number of moles. Number of moles is denoted by lowercase symbol n. We're good. We're good. Now, let us continue. Let's look at more things. Okay, calculating Kc, and why is it important to calculate Kc? Now, ensure you are able to do the following 3 steps in a Kc calculation problem. Right, now, step up your Kc expression. Check the phases of your reactants and products. Write your Kc expression. Okay, so yeah, you need to actually sort of set up. Right, so if you need to set up your Kc expression, you need to check the phases of your reactants and products, right, and be in a position to write your Kc expression there. Okay, so this is something that is very important. Use an equilibrium table. Okay, now very often we would be interested in using an equilibrium table. So the rise notation and scheme, you need to be able to draw an equilibrium table. Obviously, in our hypothetical example case, you have the A and the B as the reactants and the C and the D as the products. Okay, we're dealing with, for instance, the A is a gas, and the B is a gas, and C is a gas, and D is aqueous. The mole ratio as per balanced chemical equation. Right, so yeah, the ratio, and we're looking at the mole ratio as per balanced chemical equation. So we're looking at the mole ratio when we're having a balanced chemical equation. Initial, the I in the rise, this represents initial, where we're saying starting amount in moles of a reagent present at the beginning. Okay. Change, C.
So
Yes.
this can happen for solids. and liquids.
Yes, this is not for solids and liquids, and it is for the gases and aqueous substances. Okay, good point there. Excellent there, Noah. Right. So now there is a change in reactants or products based on the mole ratio. So, yeah, based on the mole ratio, there's going to be some potential change in reactants or products based on mole ratio. Equilibrium, E stands for equilibrium. Amount of reactant to product present at equilibrium. The E stands for equilibrium, but we're looking for the amount of reactant to product present at equilibrium. There's equilibrium again, where the concentration of reactant or product at equilibrium. We're looking for the amount. The first E is for the amount of reactant present at equilibrium, and the second E for equilibrium, at equilibrium, we're looking for the concentration. Why? Because the concentration is the ultimate. The amount, which is normally in the number of moles, etc., can obviously be can obviously be determined. But in the end, for Kc, we need the concentrations, because only the concentrations work in Kc calculations. Okay, we want to set up, set up the KC there. Okay, let's just continue and analyze these cautiously and very, very carefully. Substitute into your KC expression, substitute into your KC equation from step 1. Okay, let us look at these, and now this is very, very important, and now we have a chance to discuss this. Okay, let's look at the question that was said recently, and we're going to look at a lot of tons of past examination questions, and we have a fair chance to practice together and see how well we can do the past questions. Let us look at this question. Question 6. Right, 1 mole of pure hydrogen iodide gas, HI gas, is sealed in a 1 decimeter cubed container. Okay, in a 1 cubic decimeter container. Now, let us analyze this. Right, at 721 Kelvin temperature, equilibrium is reached according to the following balanced equation. So now you have that your hydrogen iodide gas, HI gas, is sealed in that amount of volume, 1 cubic decimeter container, at that temperature of 721 Kelvin. Okay, now let us analyze this together and see what happens. Hydrogen iodide now breaks down into hydrogen and iodine. Okay, at equilibrium. And this is balanced. Why? Because you have 2 hydrogen atoms, you have 2 iodine atoms, and obviously you also have 2 iodine, 2 hydrogen on the left. So yeah, it's all good and well. It's all very, very good and well. Let us see what we have then over here. We continue together to analyze this particular question. Okay, and the first question is clear. And the first question says, state Le Chatelier's principle. State Le Chatelier's principle. Let us state Le Chatelier's principle here. So we then say, in the statement of Le Chatelier's principle, we say when the equilibrium, right? When the equilibrium in a closed system, right? When the equilibrium in a closed system is disturbed, okay? Is disturbed, right? Let us see what we have. Is disturbed the system. The system will, right, reinstate a new equilibrium. Okay, we'll reinstate a new equilibrium. We will reinstate a new equilibrium by favoring the reaction that will cancel or oppose the disturbance. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel or oppose the disturbance, and this is called Le Chatelier's principle. It's called Le Chatelier's principle. Next question. In the next question, they're saying determine the number of moles of each of the following at equilibrium when we are dealing with, for instance, the hydrogen gas and also your hydrogen iodide gas. Right, so in the next question then, we are looking at the number of moles of the following at equilibrium. So what will be the number of moles of hydrogen be at equilibrium? So we are dealing with the number of moles of the hydrogen gas at equilibrium. Okay, it is found that 0.11 moles of iodine are present at equilibrium. So we are saying for iodine is 0.11 moles. Okay, so that in the end, then what we then have is for this one is 0.11 moles. 0.11 moles. 0.11 moles. So and you can just write like normally we just write 0.11 mole there. Okay, why? Because these are in the ratio 1:1. Okay, they're in the ratio 1:1, so we're able to see therefore at equilibrium the hydrogen the ratio is 2:1:1. So 2:1:1, so that now if you're looking for the number of moles of hydrogen iodide, or rather hydrogen alone, it would be obviously it's in the same ratio as the iodine, 1:1. So now if this iodine is actually having number of moles of 0.11, it means hydrogen also has 0.11 there. Next
Okay,
question.
so
Yes.
moles at equilibrium means the real number of moles.
Yes, moles at equilibrium recreate, yeah, definitely mean the real.
And
Um,
then
yes.
the change in moles, what does that one? Because those are the ones that are used, right?
Okay. Yeah, definitely.
The,
Yeah, definitely. We're yet to analyze the changes. Because obviously now,
because change means used up,
yes,
right?
change means used up. Yeah.
So is it going to be a different value from 0.11?
Yes. It's gonna be different from the 0.11. Okay. Yeah, but
Can
we're
you
gonna
please can
yeah,
you
we're gonna
explain the
calculate.
difference between
Yes.
the mole at equilibrium and the change
And the
in like
change,
equilibrium?
yeah, the
What's the
used
difference?
up ones. Yeah, definitely. We're gonna do an example. Okay. In particular, in this question, we're gonna see they're gonna be used ones. And we shall discuss when you get to that part of the question. But yeah, we're gonna discuss the used so that we can be able to know the number of moles at equilibrium exactly, which is sort of be the balance when we subtract the used. But we're gonna discuss that when we get to the question. Particularly, the examiner would either calculate the used or the used is given. You know. Yeah, but yeah, we shall discuss that with a clear example. Right, in 6.2.2, let us look at 6.2.2. 6.2, yes. Now, in 6.2.2, it's sort of when we get to that part of the question. It's what we're asking now. To then say, now, if you determine number of moles of each of the following at equilibrium, hydrogen iodide. Okay, we've already said hydrogen iodide, so you have the ratio 2:1:1. Okay, right. 2 moles of hydrogen iodide would be 2 moles of hydrogen iodide are in the ratio of 2:1:1. Okay, 2:1:1. Okay, so at this point, we need to determine number of moles of each of the following at equilibrium. Now, this is what you're asking, and we're discussing it now. We are then saying, if you have the used and so on, how do we filter all that in? So let us find, we are interested in number of moles of each of the following at equilibrium. Number of moles of, for instance, your hydrogen iodide used. How much would be the number of moles of hydrogen iodide used in this question? Let's find that. Okay, and then so that you can be able to know at equilibrium, we find the difference. So now the number of moles of hydrogen iodide used would become what? Okay, so it is found that 0.11 moles of hydrogen iodide are present at equilibrium. We have 0.11 of rather iodine that are present. Okay, now the ratio, if this one is iodine is 0.11, and also this one are in the ratio of 1:1. So this one here would have to be double that. Okay, so that now the used hydrogen iodide would therefore be 2 times the number of moles of iodine. So the number of moles of hydrogen iodide would therefore be, it's 2 times that of iodine, because they gave us iodine, which means that it's 2 times 0.11, and then this guy here is actually 0.22. Let's look at the number of moles of hydrogen iodide at equilibrium. Okay. Remember that now we need the number of moles at equilibrium. All right, so if we need the number of moles of hydrogen iodide at equilibrium, we then proceed to find that out. So it's going to be what then exactly happens. So we then have to say, because you're told 1 mole of pure hydrogen iodide gas. Right, so you dealt with, in the beginning, initially, you had 1 mole of hydrogen iodide, and used up were 0.22 of hydrogen iodide, and then the difference here is actually exactly 0.78 moles. 0.78 moles.
So the moles at equilibrium are the moles that were used.
Okay, the moles at equilibrium. Okay, that's a good question.
It's no, sorry, not used. It's
Yes,
the ones that are left.
the ones that are left. Well done. The ones that are
Oh,
left.
okay.
I agree with you. The ones that are left, because we subtracted the ones that are used, and then we got the ones that are left. So these are the number of moles at equilibrium. The ones that are left after subtracting the used ones. Well done. Okay, good. So yeah, we have just that kind of an example, but there are tons of examples that are here. Past exam questions. Okay, this question was set in June June 2023. Okay, this is the June 2023 exam question there. So yeah, just take note of that. Let's look at the next question. Right. So now we're looking at what happens in 6.3 of this June paper of last year, 2023. Okay, still 1 mole. Right, still 1 mole of hydrogen iodide gas is sealed in a 1 cubic decimeter container at 721 Kelvin. Equilibrium is reached according to the following balanced equation. Okay, we saw that. Here is the next question now, because we've already done up to the 6.2, and then we're looking at 6.3, yes? The equilibrium constant, which is what we call the Kc at 721 Kelvin temperature, is 0.02. Okay, the Kc is given. The temperature of the container is now increased. Okay, we change the temperature, and we've just said temperature is the only thing that changes Kc, the Kc value. But now the examiner increases it to 850 Kelvin from 720 Kelvin, the initial temperature. The equilibrium constant Kc at 850 Kelvin is 0.09. What has happened to the Kc? Because at 721, it was 0.02. At 850, it is 0.09. And we know that Kc is the concentration of the products, right? And we divide that by the concentration of the reactants. Like so, I mean, we just discussed that. So we have that Kc becomes the products divided by the concentration of the reactants. Okay, concentration of the products, concentration of the reactants. Something that we just discussed, obviously over here. The product concentration of the products divided by the reactants. The reactants are sitting in the denominator. Okay, so we awesome. We awesome. Now let's look at these here. So if this Kc has now increased to 0.09, is the forward reaction exothermic or endothermic? Because if the Kc has increased, what does it mean? The Kc is now bigger. For this Kc to become bigger, it means that the numerator must become bigger. It means that the numerator must become bigger, the denominator must a little bit become smaller, at least. Or the numerator can become bigger and the denominator remains fixed. Okay, but one possibility is therefore that because this is a reaction that is obviously at equilibrium, and therefore we expect that now if there is a change, which is the increase in temperature, when the concentration of the products increase, the concentrations of the products increase, those of the reactants, the concentration in this case of the reactant will somehow decrease there. Okay. In other words, it means therefore the forward reaction itself. Okay, we're yet to explain. But now, because they're saying fully explain your answer, so we shall do that the next question. But obviously, is the forward reaction exothermic or endothermic? Well, you're able to see therefore that the forward reaction is endothermic. The forward reaction is endothermic. So if you increase the temperature and the Kc now increases from 0.02, because the 0.02 is 721 Kelvin. At 850 Kelvin, it is 0.09. The Kc has increased with the increase in temperature. That happens. So when the temperature increases, we actually are seeing that the Kc also increases, and this happens in an endothermic reaction. Okay, can you have better ways to, or even more ways to explain that part? But let us look at the next question. So now, then the question is that, why is this? Because in 6.3.2, the examiner is saying, fully explain the answer to question 6.3.1. Explain it. Why? Why are we saying if the temperature increases and the Kc increases, then the kind of reaction we're dealing with, the forward reaction is endothermic? Why is that the case? Why? The examiner is saying, so we're going to explain that part. And here's the explanation. So to explain that, we're going to say that Kc increased. Kc increased. Okay, because the Kc increased, you can write here and say Kc increased. Right, because Kc increased, what does it mean? The concentration. The concentration of the product the concentration of the product, be it hydrogen, gas, and iodine, gas, is increased. Right, it's increased. Okay, we're going to analyze what that means in a little bit. Let me just explain here. So the concentration of the product, is, be it hydrogen and iodine, is increased. Okay, we're going to analyze once again what that means. Next, we actually can say, or we can say the concentration is what I was saying, the concentration of the reactant, the reactant being the hydrogen iodide gas, decreases. Okay, so we know that the increase in temperature, because the temperature increases from 721 Kelvin to 850 Kelvin. So the increase in temperature, favors the forward reaction, favors the forward reaction. Okay, so we can see that the increase in temperature favors the forward reaction. Why? Because the Kc increases. Okay, let's say more. One more point that is very important is actually the fact that, what does the Chatelier's principle say here? According to Le Chatelier, according to Le Chatelier, all right, according to Le Chatelier, this principle, an increase in temperature favors the endothermic reaction. Okay. Okay, let's look at that. So we continue. We continue. Right, so what does this mean? Okay. Now we are really saying here, we have to fully explain the answer in terms of, we suggested that the increase in temperature that means, or that brings about an increase in the Kc has its own implications. The temperature increased from 721 Kelvin to 850 Kelvin. That is what the temperature increased by. And the Kc increased from 0.02 to 0.09. And we're saying that if that happens to the Kc, an increase in temperature favors an increase in the Kc, it happens only if the forward reaction is endothermic. Okay, that we saw. But here are the explanations for that. So first point of actually that we need to note is that Kc increased, okay, from 0.02 to 0.09. The concentration of the product, be it hydrogen gas and iodine, is increased, right? So moreover, or the concentration of the reactant, hydrogen iodide, decreases. So you can even say here the concentrations, you can use the concentrations of the products are increased. So you can use the fact that the concentrations of the products with hydrogen iodine are actually increased, or the concentration of the reactor, the concentration of the reactant hydrogen iodide decreases. The increase in temperature favors the forward reaction. Yeah, we saw that when the temperature increases, it favors the forward reaction. How do we know it favors the forward reaction? Because the Kc increased. How does an increase in Kc show? Because we know that this is a concentration of the products. Kc is concentration of the products divided by concentration of the reactants. Right, concentration of the products divided by concentration of the reactants. So, this is what we have. So, when the Kc increases, it means the concentration of the products, increased, and the concentrations of the reactants decreased. So the increase in temperature favors the forward reaction. How does it favor the forward reaction? Because the Kc increased, and Kc increase means the products became larger in concentration, and it means therefore for them to become larger, the products in concentration, it means that the forward reaction was favored. And yeah, okay, there's more we can always say there. Right, according to Le Chatelier's principle, an increase in temperature favors the endothermic reaction. According to Le Chatelier's principle, an increase in temperature favors the endothermic reaction. Okay, because when the temperature increases, the reaction will tend to do what? According to Le Chatelier's principle, when the temperature increases, the tendency of the reaction to counter that and to reduce the temperature would happen. And therefore, it means that the forward reaction itself or the endothermic reaction is favored. Why? Because the endothermic reaction is a kind of reaction that requires heat to go on. So what it does is, if you increase the temperature, then the reaction that absorbs the heat is what is favored. If you increase the temperature, then it absorbs the heat, because then if it absorbs the heat, then it's able to go on, to proceed. Okay, let us continue. So this is the explanation. All these things are the explanation to question 6.3.2. That is the question we're discussing. Okay, let us look at the next one. Now for 8 marks, let's calculate our KC here. Let's calculate our KC for 8 marks. Calculate the mass of hydrogen iodide present at the new equilibrium at 850 Kelvin. So now we have two KC values, 0.02 at 721 Kelvin and 0.09 at 850 Kelvin. Okay, let's continue. Okay, so all right, so continue. Let's look at, yeah, we're looking at question 6.3.3. Yeah, made no space available for it. Let's do the calculation here and see what we have in 6.3.3. Right, so in 6.3.3 now, we're gonna look at the fact that this is the balanced chemical equation following the balanced equation. So it is already balanced. How do we know it's balanced? It is balanced because we're able to see the fact that we have 2 hydrogen atoms, 2 iodine atoms, and 2 hydrogen iodide atoms, the Kc. Okay, concentration of hydrogen. Okay, okay, yeah, we're taking the products and hydrogen, and then we also have our iodine, and we divide by the hydrogen iodide gas. We square this because of the number of moles of the hydrogen iodide too.
So don't you have to draw the table?
Okay, yeah, we can already sketch the table. Right, you can already sketch the table. For example, if you look at the fact that you have the hydrogen iodide gas, and you have your hydrogen gas, and you have your iodine there. The couple of things that we saw, because 1 mole of pure hydrogen iodide is sealed in that in 1 cubic decimeter container at 721 Kelvin. Okay, and obviously we know that this was the number of moles that was present in the beginning. And when that number of moles was present in the beginning, what then happened was that we actually did not quite have anything else. So you had 1 mole here in the beginning when these were not at all present in the beginning. So this was initially the case. Right. And then obviously we actually were able to make a couple of observations and do a couple of changes. And we discussed a couple of changes. And so what then changes did we actually therefore get to discuss at this point? I want us to discuss that fact. Okay, we are able to see, because there are 2 states here. Um, we saw that there was a change, right? So when we have a reaction there, and how much therefore was the change? We're looking at the rise, right? So if obviously these are a reaction and initial and the change, and we're looking at the rise. Okay, obviously there are two equilibrium values in this question, so it's something you need to take note of. But I'm going to mention what happened in the first case. So the change was, okay, it is found that 0.11 moles of hydrogen iodide are present at equilibrium. Okay, we're dealing with the 721 Kelvin. So now at that temperature, we had 0.11 present. So we saw that it's going to be 0.11 here, and then the change is going to be 0.11 here, and the change is going to be 2 times that, which is 0.22. Right. And obviously this 0.22 is 2 times 0.11. Okay. We analyze that. We continue. Right, we can draw the table this way. And we can draw some rows here. Okay, this is not very tidy, but if you just forgive me then. And then now you'd have the change as well. Okay, this is at the first equilibrium. There are two of them. There are two temperatures there, and now at each temperature has its own Kc. Now then okay, let's look at then what happens at equilibrium. The amounts at equilibrium. What were the amounts at equilibrium? So we saw that initially there was one. So you'd have therefore that at this point then at equilibrium, you then had 1 minus 0.22, which became 0.78. 0.78. 0.78. Okay, let's continue. So now, let's look at what then happens, because it's found that these are present at equilibrium. So obviously, I mean, what is being noted will therefore be the fact that you would have the 0.11. But now let's take a look at what happens here. And this happens at what temperature? At 0, at rather it's 721 Kelvin temperature. Okay, now there is another temperature at 50 Kelvin. All right, at the temperature of 850 Kelvin, let us analyze together. And obviously we're going to have a new Kc, and we need to record data for that part. The temperature is therefore increased, and we are then saying then the concentrations therefore somewhat changed. So let us analyze together and look at what the concentrations were. What were the concentrations? Right, so I'm going to look at the concentrations here. Right, so if the concentrations themselves become number of moles over volume, so you'd have 0.78 divided by 1, which is 0.78. 0.11 divided by 1, 0.11. Okay, these are concentrations, all of them. Yeah, it's 721 Kelvin. And also here you'd have 0.11 divided. Okay, because the is concentration equals number of moles over volume, but the volume is 1. 1 cubic decimeter and divide the number of moles by the what? By the volume of 1. So it is just 0.11. Now this table therefore is increased, is extended. When we're then saying the temperature then increased, then there's going to be a new extension. So there is a new equilibrium. Okay. Okay, 2 hydrogen iodide, gas, iodine. Okay, so okay, let's look. This one is going to have there's going to be concentrations. So this is the equilibrium concentration, equilibrium amount in moles, equilibrium concentration. So it's the rise. And then now, yeah. So yeah, the two equilibrium. So this is the equilibrium concentration, and this is the equilibrium number of moles. And then here, there's going to be a new equilibrium. There's going to be sort of a new equilibrium. Let's look at the new equilibrium. Okay. Right, when we have the new equilibrium, it means therefore that now the concentration of the... Okay, we saw that the products, the Kc increased, and therefore, because the Kc increased, it was a good sign that in the new equilibrium, you'd have 0.11. So what will be the new concentrations now? And that is sort of the discussion we're having. Okay, so this one is going to be 0.11 plus x. 0.11 plus x. Okay, this one is going to be 0.78 minus 2x. Okay, because of the 2 here, So this one is going to be, obviously, the equilibrium concentration is 0.78 at temperature 721 Kelvin. And then this one is at 850 Kelvin temperature. And then now the concentration of the concentrations of the reactor of the products.
So the first table is for the
721.
original.
Is the original
Oh, the
table?
original
Yes.
sentence one. Okay.
Yes. Yeah. Is the original table at 721 Kelvin? And then now there's going to be another table when you have like 850 Kelvin temperature.
So the reactants are gonna be higher. That's why you said plus X.
Yes, because then the products, because the Kc,
Okay.
yeah, the Kc is now higher. It means because
Mm.
the Kc is now higher. How is it higher? Because 0.09 before it was 0.02. So it means the concentrations of the products on the right would increase those concentrations. And we got the concentrations. What were they? There was 0.11, 0.11 of the products, and then 0.78, the concentration of the reactant here. But of the products are going to be higher because the Kc became higher. So we say plus X plus X. Why plus X? Because there's a 1 here. 1 here. In principle, we can say plus 1x, plus 1x. And then here, this one, because it's 0.78, we then say minus 2x. Okay, as I said, you can say 0.11 plus 1x. 0.11 plus, 1x, okay, is equal to the bottom one, 0.11 plus x, 0.11 plus x. Okay, the 0.78, we minus 2x, because why? Because when the right increases, the left decreases. It's not that they're gonna both increase. Okay, because the right increases, therefore the left decreases. Because the left is being used up when the other one is increasing. That is what is happening. So the increase comes from somewhere. The right increases because something is losing. The left is losing for the right to gain. So that is what happens. Let's continue right now. So in principle, then, what does this mean? It means that when we have the new equilibrium, we have the following. Okay, we have the same sort of equation here. We have a hydrogen iodide, 2 moles of it. And, okay, but you see, if we say 2 moles of hydrogen iodide, we don't mean, these are just relative number of moles. Okay, sometimes we say 2 moles of hydrogen iodide, 1 mole of hydrogen, 1 mole of um iodine. It doesn't mean that it's actually what it's those are relative moles, because 2:1:1, and these become the moles. 2:1:1, those are the moles. But doesn't mean, because we know very well that a hydrogen iodide does not have 2 moles. It has 1 mole of in the beginning, for example. On this one, at equilibrium, they had 0,1, 0,1, but the ratio is 1:1. So normally when you read here, and when the chemistry teachers read and the students, they say 1 mole of this, 1 mole of that, but doesn't mean you're dealing with 1 mole in the calculations. Okay, so the value substitute there obviously are different. So we're looking at this one. Okay, I'm looking at the new equilibrium. And then, okay, we then say that equilibrium, at the new equilibrium, there's going to be 0,11 plus 1 times x, 0,11. The 0,11 is from the previous 721 Kelvin concentrations. And then we are 0,78, and then we minus 2x. Okay, with this, then we are able to continue and solve this. And so now we have the new equilibrium, we have the equilibrium concentrations. It's the rise. We did it, sure, okay, messy, but yeah, we did the rise together there. All right, let's just do the thing, calculate. Okay, now let's do a calculation. So we are right back, and we have a Kc, concentration of the products. We divide by the reactants. Okay. Where's Kc of the products? What are the products? The products are these ones, because they increased. Why? The products increased because the Kc increased. Okay. So we have the products, which should be, okay, yeah, let's write it nicely. Let's write it nicely. So to write it nicely, we're gonna use this balanced chemical equation, and then write H2 gas, and then I2 gas, and then divided by a hydrogen iodide gas, but yeah, this one is squared. What is our Kc? Okay, so our Kc, okay, what is the hydrogen iodide? So this one here is 0,11 plus x, 0,11 plus x. We divide everything by the hydrogen. Okay, yeah, this is hydrogen and iodine. And then the hydrogen iodide, this one is 0,78 minus 2x. We square it. Why do we square it? Well, we square it because of the 2 here. Okay, we're good. Now let's see what else we're getting. Right, so we're good, and we get this one. Okay, remember that these things are happening at the new temperature of the new temperature. That's when we have a new equilibrium, and we need to calculate the hydrogen iodide present at the new equilibrium. So we're calculating the Kc at 850. Normally the examiner will say Kc at what? Okay, so we're calculating Kc at 850. But at 850 Kelvin, the Kc is 0,09. Okay, we're dealing with Kc at 850. This is a quadratic equation we need to solve. We need to solve. Okay, I know that this is a messy task. So if we say 0,09, right, so 0,09 is equal to 0,11 plus x plus x. Okay, and then we divide everything by the denominator. We had 0,78 that was reduced because when the products gain a lot, the reactants lose. That's why we have the -2. Okay, now let's do this. 0,09. Okay, we're gonna just obviously indicate this just so that you can get an idea of what's happening. 0,11 times 0,11. Okay, and then everything else, what do we do here? We can cross multiply if we want. Like I'm looking at a nicer way to do it. 0,09 and with 0,78 minus 2x, and we square this. And it's 0,11. You can write this one as a perfect square like this. Right, this is a quadratic equation. So it is 0,09. And then we square this, we square that, which is 0,78 squared. Let me just launch a calculator so that you can just have fun a little bit and just show how this thing is done. And then, right, for example, we just need to do a couple of calculations. Okay, we're saying 0,78, we square it, so 0.78 squared, which is this one, is 0,61. Okay, let us write this one is 0,61. So it is 0,61. Okay, we're squaring this one. Minus this times 2 minus 2 times 2. It's minus 4 times 0,78. Try to be a little bit faster to do this one here. Okay, let's just do it. Okay, this exam was June. Right, so it's 0,78 times 2 times 2. 0,78 times minus 2 times 2. Okay, the minus, I've not put it on paper in purpose, but which is 3,12. So it's 3,12x negative 3,12x plus, then you square this one, which is going to be plus 4x squared is equal to, okay, we need to square this guy also. Okay, let's the calculator again. I'm going to finish this quickly. Okay, the next thing is obviously we need to deal with this one. Let's just square this out. To square this out, you need to say 0,11 times itself. Okay. 0,01. 0,01. Okay. So you'd have 0, did you say? Did you say, you said 0,01? Yeah. You said 0,01. Yep. Okay. For this one. Then 2 times this. 0,22x plus x squared. Okay. Let us have a little bit of fun just doing this KC calculation, then we look at another exam paper. Okay, now let us look at this one. 0,09 times 0,61. Okay, which is 0,055. Can write it like that, more accurate, 0,055. 0,055. 0,055. Okay, taking just one more decimal place. Minus 0,09 times 3,12. Let's check. 0.09 times 3.12 0.28 0.28x 0.09 by 4. Okay. 0.09 by 4. 0.36. 0.36. 0.36x squared, which is 0.01 plus 0, 0.22x plus x squared. Okay, now let us do these quickly. So we're going to say, I'm not going to waste a lot of time there. So it's x squared minus 0.36. Right, so if we then say minus 1, yeah, 0.64, 0.64x squared, which is this guy. Okay, 0.22 plus 0.28. 0.22 plus 0.28, which is 0.50. X, okay, this one together with this one, 0.01. Okay. Okay, we shall just finish this part. Okay, just doing some algebra here. Okay, so we have 0.01, and then we minus 0.055 minus 0.045. Mm-hmm, mm-hmm, mm-hmm. Minus 0.0. Is it like that? Okay, just checking there. Minus 0.045. Okay, and this equals 0. Now, this is what we got. And then it's a quadratic. So x is minus b plus or minus the square root for c over 2a 0.050 0.50, you square it. A is 0.64. Let's write here. X equals minus 0.50 plus or minus the square root. Okay, plus or minus the square root of the b, 0.50, u square minus 4a, 0.64. The c is minus 0.045 divided by twice a, which is 0.64. Okay, now let us quickly do this one. Okay. Okay. 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 。 。 。 。 。 。 . 。 。 。 。 。 。 。 。 。 。 。 。 . 。 . 。 。 Now, let's just do everything under the square root. Okay, under the square root, we have 0.5 squared minus 4 times 0.64 times negative 0.045. 0.3652. 0.3652. Okay. 0.3652 square root divided by that one, which would be the 2 times 0.34, 0.64. Okay, we're going to finish this calculation, please. You don't need a lot of writing here, ordinarily. So 0.3652, and then you take the square root of the answer. Okay, which would be 0.604. 0.604, you divide by, okay, it's not just 2 here, please. It is something. 2 times 0.64, and we just need to, yeah, okay. So you're spending lots of time doing algebra. 2 by 0.64. Right, which is 1.28 in the denominator. So this one is going to be exactly 1.28. Okay, 1.28 also here. 1.28. 1.28. Okay, so we can have negative, negative, but we're dealing with concentration, so we shall only take the positive so that our x is the same as, let's just do it quickly. Okay. So if we do this, we're gonna have this, and we're gonna have the minus 0.50 plus 0.6. Okay, 1.28. Okay. We're taking only the plus because the other one is going to be negative concentration. We don't want it. Right, so it is 0. Okay, let's check this one. 0.08. Right, which is 0.08. Yeah, that's fine. So we're therefore getting 0.08. Okay, so it is 0.08, and that is what we're getting. But remember that we're dealing with this one, and this one was at the new equilibrium. It was 0.11 plus. Okay, we remember that one. It was 0.11 plus x, 0.11 plus x, and this one was 0.78 minus 2x. Right, so if we get the x, then we're interested in we need to calculate the mass of the hydrogen iodide present at the new equilibrium. But now, something that remains extremely important for us is to then say, what will this be? Okay, we need the concentration here. We need the concentration of this. So you can write like this. This is very, very standard. We need the concentration of the hydrogen iodide at equilibrium, which is 0.78 minus 2 times the x we've already got, Okay, this X is 0.78, but if you do it, there's a more accurate result, which is 0.0775. If you take like more decimal places. Okay, so I'm gonna use this more accurate one, because yeah, this one is rounded off. Okay, now therefore for this hydrogen iodide, therefore you'd have the 0.78 minus 2 times 0.0775. Okay, if you use a calculator, then whatever you're getting is 0.63. 0.63 moles per decimeter cubed. Okay. So now what is the... Okay, this is the equilibrium concentration of a hydrogen iodide at equilibrium. It is 0.63. But we don't want just these. We want the mass. So we have got the concentration of a hydrogen iodide at equilibrium, and it is actually 0.63 moles per decimeter cubed. Okay, we want the mass. But we know therefore that at this point, concentration is number of moles over volume. That's the formula. We want the number of moles to find the mass. So we cross multiply here so that the number of moles of hydrogen iodide would therefore be the same as CV, cross multiply N equals CV. The concentration is this one of hydrogen iodide, which is 0.63. And the volume is 1. So you have 1 cubic decimeter. Therefore, this is 0.63. The number of moles, it is the, when you write the mole. Okay, but if you do it very accurately, you're able to get that this is 0.63. But you see, this 0.63, just going to mention, is 0.63, but this 0.63, if you do it very carefully here, 0.78 minus 2 times that, you'd realize that it is actually, can just show something more practical here than just show with the calculator where these answers are coming from. So you'd say 0.78 minus 2 times 0.0775. Okay, we don't see 0.63, but you can see that it is actually 0.625. 0.625 moles per decimeter cubed. Okay, which is rounded off to 0.63. So, but now you're going to come here and also here, the more accurate answer would be 0.625 times 1, which is 0.63. But yeah, we have a rounded off result. So we want the mass, so which means therefore now we're going to do the mass. You can do it in red. It's the final answer. So we're interested in the mass. What is this? Number of moles is mass over molar mass. Mass, hydrogen iodide. Okay, cross multiply here. Mass is hydrogen iodide, which is number of moles times the molar mass. So which means the mass of the hydrogen iodide is the number of moles. We can use 0.63 or 0.625. And then we multiply by the molar mass. Okay, what is the molar mass of the a hydrogen iodide. It's the molar mass of hydrogen. Okay, this one I'm going to write it is 128. Okay, from the periodic table, but it is the molar mass of hydrogen plus the molar mass of iodine. Okay, the total is, this is from the periodic table. I know you know that. So that in the end, then is 128, and it is actually, therefore, if you multiply 0.63 by 128, what we're getting is 80.64 grams. Okay, we have found the mass of the hydrogen iodide. Any discussion that you can bring, anything else you can mention here? But now because we have to calculate the mass of hydrogen iodide present at the new equilibrium at 850 Kelvin, we found it to be exactly 80.64 grams. Any question or any suggestion, no?
No questions.
Okay, it's a bit long. Okay, and boring. Let's look at the next question. Right, here's the next question. The next question is very, very nice and easy. And so now, if you look at this very, very carefully, it's an awesome, awesome question. I want us to look at the graphs and analyze the graphs. I mean, sometimes the examiners, they set graphs. This question we're looking at was set in November last year. Okay. It was set in November last year, November 2023, and we're taking a look at it and seeing what the students had to do in last year's November paper. Okay, now, question 6. This question came from November 2023, chemistry paper. Consider the following hypothetical reaction reaching equilibrium in a 4 cubic decimeter closed container at 150 degrees Celsius temperature. And obviously it is a hypothetical reaction. What is it? Okay, so you have 2 moles of AB gas, which break down and undergo dissociation into A2 gas plus B2 gas. And all these are actually gases, and therefore this is a hypothetical reaction. Okay, these are in the gaseous state. Okay. Right, the graph below shows the changes in the amount of reactants and products over time. Okay, so this shows the number of moles of the changes in the amounts of. Okay, once the examiner uses the word amount, so we're dealing with moles of reactants and products over time. You can see, therefore, that here the moles decrease, here increase, etc., and here they are constant, etc., etc. And they fluctuate. Okay, good. Let's answer the questions that they brought for the November 2023 students. Write down the meaning of the term reversible reaction. What kind of a reaction is reversible? 1 mark. This is what they asked November last year. Write down the meaning of the term reversible reaction. What is a reversible reaction? A reaction where products can be, okay, let's just analyze this one. So we are saying a reaction where products can be converted back. Okay, we're talking back, converted back to reactants. Okay, let us look at what this means. And vice versa. Okay, analyze this with me. Okay, so we are saying, consider the following hypothetical reaction reaching equilibrium in a 4 cubic decimeter closed container at 150 degrees Celsius temperature. Write down the meaning of the term reversible reaction. A reaction where products can be converted back to reactants. So you have the products, and these can be converted back to reactants this means that you have a reversible reaction because you can be able to convert the product back to reactants. Okay. State Le Chatelier's principle. Okay, let us write the statement of this one. It comes most of the time. Please, this one it's 2 marks. You can be rest assured, always memorize it. Let's just write it again. And when the equilibrium, right, when the equilibrium in a closed system, is disturbed, the system will reinstate a new equilibrium. Will reinstate a new equilibrium by favoring the reaction that will cancel, stroke, oppose the disturbance. This is Le Chatelier's principle. Disturbance. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel or oppose the disturbance. Learn it and memorize it. Next question. Right. Now we have the information above. A change was made to the equilibrium mixture at t equals 80 seconds. So t is time in seconds. And now a change was made to the equilibrium mixture at this time of 80. At 80, a change was made. Okay, let us see what the examiner is saying. Write down the change. Write down the change made at t equals 80 seconds. What change was made at t equals 80 seconds? Right, so what are you able to see here in particular? Okay, the AB, you can be able to see the AB which reflect the reactants. So you can see that the concentration of the reactants from at 80 seconds, there's a sudden increase in the number of moles of the AB, but also you're able to see that the number of moles of the A2 decrease just immediately after 80, but also of the B2 also decrease. So you can see that A2 and B2 decrease, so the products decrease when the reactants, the reactant AB happens to increase or increases. Okay, why? I write down the change because these are gases. And this is at a temperature of 150 degrees Celsius temperature. What was the change that suddenly increased this increased this one and decreased that? Okay, so there was a change that was conducted and it decreased A2, decreased B2, but increased AB. Increased AB, the amount. The amount stroke concentration of A2 was increased. Okay. So this is the response. Or you can say that, at this point, A2 gas was added. To the container. A2 gas was added to container. So in other words, the amount or concentration of A2 was increased. Okay, because now, if you look very, very carefully in 6 point, write down the change at this. What we are seeing is that suddenly, the fact that the products themselves decreased in concentration and the AB increased in concentration is actually a clear sign that what happens is, according to Le Chatelier's principle, if you disturb the equilibrium, what then the equilibrium does is to counter the change. So we're then saying the amount of concentration of A2 was increased. So if you attempt to increase the concentration of A2, then according to the Chatellier's principle, this will tend to decrease that, counter that increase. Okay, so we continue. We continue. We continue. We continue. Okay. So a change was made to the equilibrium mixture at T equals 80 seconds. And once again, write down the change made at 80. At 80, once again, what are we seeing? We are seeing a sudden decrease in the number of moles of the products. And that actually can be justified by saying the amount or concentration of A2 was increased, because if it is increased, then okay, or we can say A2 was added to the container, because if it is added to the container, then suddenly what happens is that the A2 will then tend to decrease as the AB itself would then increase to establish a new equilibrium, there. Let's look at the next question. Okay, the next question says, use the Chatellier's principle to explain how the system reacts to this change. Okay, this is the explanation. Use the Chatellier's principle to explain how the system reacts to this change. Right, so in 6.3.2, the first thing was going to say increase in A2. Increase in A2, a concentration favors the reaction that uses or decreases. Okay, we continue. Okay, when I look at what I'm writing here, a decrease is the amount. Okay, we're gonna analyze together what this means. The amount, or sort of the concentration of A2. Right, so next we can say the reverse reaction is favored. The reverse reaction, okay, is favored. Okay, let's look at this one, please. Okay, so use the Chatellier's principle to explain how the system reacts to this change. Now, increase in A2 or concentration favors the reaction that uses or decreases the amount of concentration of A2, the reverse reaction is favored. So in other words, you can see that suddenly we saw that AB increased and there was A2A and A2 and B2 went down. So increase in A2, concentration favors the reaction that uses or decreases the amount of concentration of A2. The reverse reaction is favored. You can see the reverse reaction was favored because suddenly there was an increase in the reactant, and therefore this means that obviously an increase in A2 or concentration of A2 would favors the reaction that uses or decreases the amount of A2. And which reaction would decrease the amount of A2? It's the reverse reaction because it actually was increasing there. So we're able to see therefore that an increase in the amount of number of moles of AB meant that obviously the reverse was favored, and that the reverse is favored if only we increase these guys. We increase the A2 and it would favor the reverse, because the reverse would then use the A2 up and sort of decrease it. Let's look at the next question quickly. I'm aware of the time. Okay, so we're done with that. Let's calculate the equilibrium constant Kc at 120 seconds. Right, so in 6.4, we already have the hypothetical, hypothetical reaction. So we have that our Kc is actually exactly A2, B2, you divide everything by AB squared. Okay. So now what then is the meaning of all these here? So I want to calculate the Kc at 120. Everything is on the graph. Okay, so the graphs normally make life way too easy. But we remember that if we need to find the concentration of A2, okay, because we know that concentration is number of moles of a volume, okay, you can do concentration of A2. And then now we would do, okay, we can see that the volume is this one. It's 4, so that we have concentration is number of moles of a volume. Okay, A2. At the at time 120 seconds. Okay, 120 seconds. Let's read the moles. Like if we want to read the moles of A2, okay, because we want to deal with A2 here. So A2 is there, and the moles are exactly 8. Okay, the moles are 8. So we're going to do 8 over 4. Right, which is actually 2 moles per decimeter cubed. Okay, let's do the other thing. This one, concentration of B2, number of moles on volume. What is number of moles? B2. You have the number of moles, which is exactly 2 over 4, 0.5 moles per decimeter cubed. Okay, we're gonna just substitute everything quickly, just now. And then we're gonna do another concentration of the AB is number of moles on volume. And okay, let's deal with AB, but at 120 seconds, AB is this guy here, and it's exactly 10. So we have 10 divided by the volume, 4. And therefore, this one is like 5 over 2, which is 2.5. 2.5 moles per decimeter cubed. Okay, A2 is 2. B2 is 0.5. It's 1/2. And then AB is 2.5 square. And therefore, we have the Kc is actually that one. Let's just do the calculation together. Let's launch a calculator quickly. Okay, I can see the time, please. Just cruising to get this So let's do this. So you have 2 times 0.5. You divide by the denominator, which is 2.5, and then you square it like this, 0.16. Okay, 0.16. So dimensionless, no units for the KC, but it is actually exactly 0.16 there. And therefore, this should be the answer to this question. Let's look at the next point. Okay. Okay, now at t equals 130 seconds. Okay, t equals 130 seconds. Okay, this one is 120, and then 130 is going to be here. The temperature of the system is decreased to 100 degrees Celsius. Draw a potential energy diagram for this reaction. Okay, so for this reaction now, let us draw a potential energy diagram for this reaction. So if we then saying at t equals 130 seconds, the temperature of the system is decreased. So if you decrease the temperature of the system, what then do we expect? So we really expect that from grade 11, this is gonna be sort of the graph there. Okay, let me just draw a clearer graph. Okay, from grade 11, this is sort of gonna be is gonna be the graph. Yeah. So which means that the cause of reaction, potential energy, potential energy. Okay. So now, because this kind of a reaction is such that what we are able to see the potential energy of the products themselves versus the potential energy of the reactants. Right. So we're able to then see that in view of the fact that the potential energy of the products will therefore be sort of higher than the potential energy of the reactants. And this will sort of be the potential energy for this particular reaction there. Okay, for example, what then are you able to see? Because we are saying that the temperature is decreased to this. Right, so if it is decreased to that because it was initially 150 degrees Celsius there. But now if it is dropped to 100 degrees Celsius, what we're then able to see that is the potential energy of the product is higher than the potential energy of the reactant. So the reactants will therefore have a lesser potential energy there. Okay, and so this is actually what then becomes noticeable there. And you can actually obviously we'll have more elaborations on this particular note. Okay, I will elaborate more on this in a little bit, but this will sort of be the potential energy diagram for this particular reaction there, because yeah, there's more detail we're gonna actually state. But let us first look at 6.5.2. Will the equilibrium Kc at 100 degrees Celsius be greater than, less than, or equal to the Kc at 150? Okay, this is very important. What is going to happen to the Kc? Right, so let us look at 6.5.2. Right, so if you look at 6.5.2, we note that now we're looking at the Kc. It will be less than. It will be less than the amount stroke concentration of products B2, A2 decreases. Okay. Right. So now we are then saying, will the equilibrium constant Kc at 100 degrees Celsius be greater than, less than, or equal to the Kc at 150? Remember, there was Kc at 150, then now there's Kc at 100 degrees Celsius. So it will be less than. It will certainly be less than. Right. So we are choosing less than. And we obviously proceed to um, explain the answer. Um, in our explanation, so this one would be, the less than would be 1 mark and this would be 2 marks, and the marks would balance to 3. But it will be less than. Why? Explain why it will be less than. Because the amount of concentration of products B2 and A2 decreases. Obviously, we are able to see that the concentration of the A2 and that decreases. Okay. And also, I mean, we're looking at T equals 130 seconds. A2 and B2 decrease. So the fact that the concentration of the B2 and the A2 decrease means that if you decrease the temperature, also the products or the concentration of the products decrease there. Okay, and also you're able to see that the concentration of AP. So you can also say here, so I mean, you can be able to guess if this reaction is endothermic or exothermic. Okay. Right. So you can be able to guess if the reaction is endothermic or exothermic, because if the temperature is decreased at 130, the A2 and the B2 go down. Okay. So it means, therefore, you really can see that contrary to the fact that in the initial example we did where the Kc was 0.02 721 Kelvin temperature, I just want to put this analogy here. Okay, and then now, okay, I'm finishing, please. And then the Kc became 0.09 at 850 Kelvin temperature. We actually were able to observe that when the temperature increased, the Kc increased, and that meant that the forward reaction was endothermic, because it actually, had the Kc increasing with an increase in temperature. So now you're able to see that at this point, whenever the temperature itself was suddenly decreased, you can see, therefore, that the A2 and B2 go down, and that means the amount of concentration of the products decreases. The amount of concentration of reactants amount, stroke concentration. Okay, I want to write something else. Just a sec. Okay, there are many ways to write this. So you can always say amount or concentration of reactants, which is AB, right, increases. Amount of concentration of the, okay, we can see that the AB increases. And it means that the reactant increases when the products tend to decrease there. Okay, and also you can say that you can also say that the reverse reaction is favored. the reverse reaction is favored, or the reverse reaction is favored. Why? Because the reactant increases, or you can go on to say the equilibrium. The equilibrium position shifts to the left. To the left. The equilibrium position shifts to the left. Okay, the increase in the AB concentration means that the equilibrium position shifts to the left. Okay, I want to make a comment before we conclude our discussion here. Right, so right, right. Okay, I'll just go with you now. Something that I want to make as a comment here, as part of our learning. Right. So I want to mention some properties that you you know you would not you just need to remember from grade 11. So I was looking at this potential energy diagram. This is enough to draw in the exam, but there's more that you can do from grade 11, because, for example, so this is the endothermic endothermic energy diagram. Endothermic energy diagram. So if you have A plus B, C plus D, and then here we have what we call the transition step. Okay, I know that, yeah, transition step. Okay, so I will, okay, this would be, let me use A. Yeah, you wanted to use A and B as reactants, and then, but here we can use the reactants. The reactant is only one. You can just say AB, and the product A2 plus B2. Okay, this is the endothermic potential energy diagram. Endothermic potential energy diagram. Okay, let's look at a couple of things. I want to add some information here. Okay, we will remember from grade 11, when we're still small, that this was the activation energy, and then this one here was the, okay, this one, what we call the activation energy. Okay, activation energy. I'm just, okay, right. So is the endothermic potential energy diagram. Okay, it's like this. And then, okay, we make a little bit of an error here. And then here, what we put the enthalpy change. Enthalpy. Enthalpy change, which is like delta H. Okay, this is the enthalpy change. Okay, I know this is very untidy. Okay, this would be sort of the products. Right, so it will sort of become the products, and then the reactants as well. The reactants, okay, reactants here, and then the products there. Enthalpy change, so this would be our friend, delta H. And this becomes the reaction coordinate. Reaction coordinate, and then this becomes the energy. Okay. So, okay, there's something that I want to mention here is something very important. Okay, I'm concluding our discussion, please. And therefore, The opposite becomes very, very true when you are dealing with the this is for the endothermic, where you have that the concentration of the potential energy of the products is certainly higher than the potential energy of the reactants. And then obviously with exothermic, it would be the opposite, where the products will have less of the potential energy and the reactants will have a greater potential energy there. Okay, I want to see what else is there. Okay. Okay. Now let's look at quickly. We're finishing, please. I know time is against us. Well, I'm just want to make one last comment here. Okay, this is the very last question. The initial reaction now takes place in the presence of a catalyst at 150 degrees Celsius. At 150 degrees Celsius, which is here, there is a catalyst. Describe the changes that will be observed on the graph between t equals 0 and t equals 60. T equals 0 and t equals 60. Let us discuss this. I'm going to just discuss this quickly. All right, something that is very important, the marks are 3. So you would say as your answer to 6.6 would refer to the changes or the gradients. Right. So you would note that the gradients of all 3 curves will be steeper, and reach the same equilibrium values. Right, equilibrium values. Gradients of all 3 curves will be steeper and reach the same equilibrium values. So in other words, obviously we're saying the initial reaction now takes place in the presence of a catalyst at 150. Okay, so obviously it was the temperature was initially 150. But what has changed now is just that it is in the presence of a catalyst. So if a catalyst is added, just to describe the changes that will be observed on the graph between t equals 0 and t equals 60, if a catalyst is added, right, so we're saying that the gradients of all 3 curves will be steeper and reach the same equilibrium values. Okay, so now, why is this? Because now the gradients will be steeper, because it would mean that a catalyst, what does a catalyst do? It speeds up the reaction without taking part. So if it speeds it up, it means that the gradients will be steeper between this 0 and up to 60. So the gradients will be steeper. And then steeper. So in other words, they would quickly, equilibrium is going to be reached. We're going to reach the equilibrium quicker than without the catalyst. But yet, they're going to reach the same equilibrium values there. Okay, so this is sort of the difference when the catalyst is essentially added in this case. And this is the last question. This is the last question. Okay, this will be another exam paper. Okay, any comment now? I think that obviously this will be enough for today, and then we will discuss, then we'll see what else we need to discuss. Any question? Any
No,
question?
no.
Okay, I know you're tired a little bit. Okay, you have seen these things and you need to rest, you need to relax a little bit. Okay, thanks for joining us now, and we'll discuss on WhatsApp. Yeah, we'll have more plans to learn even before we meet next weekend. Okay, but thanks, yeah, thanks a lot, Neo. Take a deep
Okay,
breath.
thank you,
Yeah,
bye.
okay, thanks. Drink water and relax.
Bye.
Okay, thanks. Bye, Neo.